everyone and welcome to CEC Gurukul live lectures. I am Neeti Bhutani from Hindu College, University of Delhi, and you are watching the 12th lecture in the series Mathematical Methods for Economics. In the last couple of lectures, we talked about linear functions and quadratic functions, and we also went over some economic applications relating to these functions. It is now time to bring in cubic functions into the picture, as also a general discussion of polynomials. Today's lecture will specifically cover topics like integer roots, remainder theorem or the factor theorem, and if time permits, we'll also talk about the multiplicity of roots. So these are the learning outcomes that we will focus on in today's lecture. So first of all, what is a cubic function? A cubic function is of the form f of x equal to ax cubed plus bx squared plus c times x plus d, where a, b, c and d are constants, and in addition we will also impose the restriction that the parameter a, which you see here, which is a coefficient of x cubed, this is not equal to 0, because if a is equal to 0, then this first term here in the function will vanish, and this is something that we don't want, because since we are talking of a cubic function, we want the highest degree of x to be 3 here. Now to start, let us first take a look at what the graphs of cubic functions look like. I'll give you a general sense of these graphs. And depending on the parameters a, b, c and d, the values that the parameters a, b, c and d take, the graphs of cubic functions assume different values, assume different shapes, Ideally, I would like to bring in some differential calculus to explain the shapes of these functions, but because we haven't yet introduced the idea of a derivative in this series, I will just give you a general sense of what the graphs of cubic functions look like, what different shapes they can take. And to see this, one feature that is generic to the shapes of cubic functions, the graphs of cubic functions, is that if you see how these graphs are shaped, cubic functions either have two turning points or no turning point. But to see this, let us first understand what we mean by a turning point. A turning point is exactly what the word turning point, what the phrase turning point conveys. So basically, if we have a turning point, then the graph can rise to the left of the turning point and fall to the right of that point. Alternatively, it could even fall to the left of the turning point and rise to the right of the turning point. So if you look at the two graphs here on this slide, for example, take a look at this point A in the first graph on the left. Here you have a situation where the graph rises to the left of A, please follow my cursor, and then falls to the right of A. Similarly, in the second graph also, if you take a look at this point B where my cursor is pointing, the graph rises to the left of B and then falls to the right of B. So basically here we are talking of bends in the graph, and if you see, what is common between points A and B is that the slope changes sign. If you look at point A, the slope changes sign from positive to negative as we pass through A, and similarly the same thing happens for B. So this is characteristic of a turning point, and for those of you who are familiar with differential calculus, you will identify these 2 points A and B as local maximum points, or points where the function changes from increasing to decreasing. Similarly, in these two graphs, the points C and D also correspond to turning points. Here we have that the graph falls to the left of C and rises to the right of C. And similarly, this is the same thing that happens with D. In other words, the slope changes from negative to positive as we pass through C. And similarly for D. Again, if you're familiar with differential calculus, you'll associate these points C and D with local minimum points, or points where the function changes from decreasing to increasing. So the point here is, the upshot of this discussion is that if you look at both these graphs on this slide, each graph here has two turning points. So the first graph has two turning points, A and C. The second graph also has two turning points, B and D. Alternatively, it is also possible that a cubic function may have no turning point. So for example, if you look at this graph on the left, which also happens to be the graph of x cubed, here there is no turning point. Now some of you might think that this the curve at the origin, it may seem like it's taking a turn, but actually it's not, because as per our definition of a turning point, the slope must change sign. And here if you look on both the left and the right of the origin, the slope of the curve is positive. So this is a graph which does not have any turning point, and similarly the second graph here also does not have any turning point. So this is a feature which is generic to cubic function graphs. Now there is another feature that we can highlight for these graphs. Let's go back one slide again. And this feature is in terms of, it can be explained in terms of the end behavior of these graphs. So for example, take a look at this first graph. This graph, it tends to infinity as x tends to infinity, and at the other end, as x tends to minus infinity, it tends to minus infinity. So this is like down-up behavior. So it is tending to minus infinity at one end and tending to plus infinity at the other end. The other graph here is tending to plus infinity on the end which is towards the left, and tending to minus infinity on the other end. Now this is also a feature of cubic function graphs, but it is not generic to cubic functions. It is something which is characteristic of a polynomial where the leading term has an odd exponent. So because here we are dealing with an x cube where the power is odd, the highest exponent is odd, that is why you have this kind of an end behavior. It is down up or up down. Similarly, you can see in these two graphs also, here the graph tends to plus infinity at one end and minus infinity on the other. So it's a down-up kind of movement, end behavior. And here you have an up-down kind of end behavior. And this is also another feature that you can identify with when you look at cubic function, the graphs of cubic functions. And this is actually in contrast with what you would see in quadratic functions. If you remember, if you've seen the lecture on quadratic functions in this series, we said that graphically quadratic functions are represented by parabolas, either a parabola that opens upwards or a parabola that opens downwards. And here you can see on this slide that for such a function where the highest degree that x takes is even, in this case, if the function, if the graph is opening upwards, if the parabola is opening upwards, then the end behavior on both ends is up, up. And similarly, if the parabola is opening downwards, then you see that the graph tends to minus infinity on both ends. So this is something which is typical of quadratic functions or polynomials where you have an even degree. Right. So now let's talk a little bit about why cubic functions are relevant for us and where exactly cubic functions are used in economics. I'll give you one or two examples. If you have been following this series, a couple of lectures before this one, I talked about, this was a lecture on titled Functions of One Variable. I talked about the total cost function, which tells us the total cost associated with producing Q units of the output. So if we represent it by, let's say, C of Q represents our total cost function. Tells us the total cost of producing Q units of the output. Now, the question is, what kind of a cubic function could we use here? I've used a cubic function on this slide to reflect this cost function, and typically this is the case in economics. In economics, cost functions are conventionally represented through a cubic function. But this does not mean that you could just do with any cubic function. There are certain features that must be true for the graph that we draw, because the cubic function has to capture a valid cost function. It has to make economic sense. And let's see what those features are, and these are reflected in, also in the graph that I've drawn. The first feature is that if you look on the horizontal axis, I have output represented by Q. On the vertical axis, I have cost represented by C. So here, because neither Q nor the cost can be negative, both C and Q have to be non-negative, we have to restrict ourselves to the first quadrant. So the graph has to be in the first quadrant. Also, let's suppose at Q equal to 0, you incur a certain amount of fixed expenditure, some fixed cost which is independent of the level of output. Then that would mean that there would be a vertical intercept that would be that would have to be shown here on the graph, which you can see here where my arrow is pointing. Here C of 0 is clearly positive, and that indicates the fixed expenditure incurred at Q equal to 0. Also, another feature of this graph is that this graph C of Q, it has to be upward sloping throughout. Okay, so this is to say that every time Q increases, the total cost will also increase. Total cost increases with every increase in Q. Also, it's not just that the curve is upward sloping throughout. There's also a certain pattern in the way the curve slopes upwards. So if you follow my pointer here, you'll see that first the costs increase at a decreasing rate. So if you see here, the curve kind of starts flattening. So costs increase at a decreasing rate, and this actually could be attributed to, let's say, a better utilization of the fixed capital. But at higher levels of output, costs start increasing at an increasing rate, and this is what I'm showing here in this segment of the cost function. So these are the features that must be captured through a cubic function, and this is exactly how a cost function would look in any economics textbook. Now here, let's take a look at another example. Again, I've used a cubic function to reflect what is known as the total product function, the total product curve, or the total product function, which is something you must have studied in your the basic microeconomic theory class. And here I've shown you that in this case, total product first increases at an increasing rate, then at a decreasing rate. It reaches a maximum and then it declines. Here total product is plotted as a function of labor, the labor employed, which is my variable factor, and you can see here it first increases at an increasing rate, then decreasing rate, reaches a maximum, and then it starts falling. And this is exactly what you would see even in economic textbooks. So these are the examples that I have from economics, and so in this sense cubic functions are very helpful while doing our analysis our theoretical analysis in economics. Now, whether we talk of linear functions or quadratic functions or cubic functions, these are all examples of polynomials. A linear function in particular is a polynomial of degree 1, a quadratic function is a polynomial of degree 2, and then a cubic function is a polynomial of degree 3. In general, we can define a polynomial of degree n, and let's represent it as p of x, which is then given by a sub n times x to the power n. And here we'll assume that n is a non-negative integer, n is strictly greater than 0. So the polynomial is a sub n x to the power n plus a sub n minus 1 x to the power n minus 1, and so on till a2 times x squared plus a1 times x plus a naught. Here all these coefficients, the a's, are all constants, and because we are talking of a polynomial of degree n, we'll assume that this coefficient, which is also known as a leading coefficient, a sub n, is not equal to 0. In addition, if we talk of the domain of a polynomial, of any general polynomial, the domain of any polynomial is the entire x-axis. So it's minus infinity to infinity. And here I just have on this slide just some names, titles for polynomials of degree 4 and 5 also. So 4 would be a quartic polynomial, and a polynomial of degree 5 would be called quintic. So these are just names that you could familiarize yourself with. Okay, so the next thing that we're going to do is we'll talk a little bit about what are known as integer roots. Now, very often when we work on problems relating to polynomials, it is quite helpful to have information on what the roots of the polynomial are, or what the zeros of the polynomial are. That is where you have the x intercept or intercepts. And the method that I'm going to explain, actually, because sometimes, suppose for example, you want to, let's say, factorize a polynomial, then it actually might be helpful to even if you know one root of the polynomial, that would give you a head start. So in that sense, it's good to be able to know at least one root of the polynomial or some of the roots. And what I'm going to do is I'm going to talk about this method which will help you identify the integer roots, the roots which are integers. We are restricting ourselves here to integers, which are roots of the cubic equation. So let's take this example. Suppose our equation is x cubed plus 2x squared minus 5x minus 6 equal to 0. Now, this is the same thing as saying x cubed plus 2x squared minus 5x is equal to 6. Now, let us suppose that our integer that satisfies this equation, the integer root, is represented by x naught, x sub 0 or x naught. Then it must be true that x naught must satisfy this equation, right? And after taking x common on the left hand side, my equation becomes x naught times x naught squared plus 2x naught minus 5 is equal to 6. Okay. Now notice here in this equation, because we are assuming that x naught is an integer, then clearly x naught squared must also be an integer. So should 2x naught will also be an integer, and in that sense x naught squared plus 2x naught minus 5 would also be an integer. Now, because you are multiplying an integer with another integer to get 6, it must be true that 6 must be divisible by both these expressions, both x naught and x naught squared plus 2x naught minus 5. In other words, if x naught is an integer, then it must be a factor of 6. 6 must be divisible by x naught, in the sense that if you divide 6 by x naught, you should get a remainder of 0. So x naught must be a factor of 6. So possible values that x naught can take, so these are the candidates for our integer roots, because we are looking for factors of 6. The integer root can only be a factor of 6. So our possible candidates for integer roots would be plus minus 1, plus minus 2, plus minus 3 and plus minus 6. So these are our possible candidates for integer roots. And now what we're going to do is we're going to substitute each one of these values into the left hand side of the equation, and if we get a 6 on the left hand side, we will claim that that value is an integer root. So let's start this process. Let's take the value 1. If x naught is equal to 1, then my left hand side becomes 1 times 1 plus 2 minus 5, which is then 1 times minus 2, which is minus 2. Now, if x naught is equal to minus 1, then our left hand side becomes minus 1 times x naught squared is 1 plus 2x naught, which is minus 2 minus 5, and then that will give us 1 minus 2 is minus 1 minus 5 is minus 6 times minus 1, which is 6, and that then would give us one of our integer roots, which is minus 1. Similarly, if x naught is equal to 2, if you substitute on the left hand side, you will get 2 times 4 plus 4 minus 5, and actually these are substitutions, very simple substitutions. You can try them even before you hear this lecture out. So here you again see that on the left hand side you will get 6 after substituting x naught equal to 2. So this is another integer root that I have highlighted in pink here. Now let's put x naught equal to minus 2. That's also a possible integer root, but the problem here is that once we substitute minus 2, our left hand side becomes minus 2 times 4 plus 2 times minus 2 is minus 4 minus 5, which is then it's going to be plus 10. Okay, what happens if we substitute x naught equal to 3? That then gives us on the left hand side, you can check on your own, that gives us a minus 6. And finally, if we substitute x naught equal to minus 3, our left hand side becomes minus 3 times 9, x naught squared is 9, plus 2x naught, which is minus 6, and then minus 5. So in the brackets we have 9 minus 6, which is 3, 3 minus 5 minus 2, and minus 2 times minus 3 outside the brackets is nothing but 6. So here we have seen that there are 3 integer roots of the equation x cubed plus 2x squared plus minus 5x minus 6 equal to 0, and those integer roots are x equal to minus 1, 2 and minus 3. Right, so let me talk a little bit about the main theorem that is at work here. The main result for integer roots states, suppose that an minus 1 and so on till a1, a0 are integers. Please note here these all these constants have to be integers. Then all possible integer roots of the equation a sub n x to the power n plus a sub n minus 1 x to the power n minus 1 and so on till a1x plus a0 equal to 0. For this equation, all possible integer roots must be factors of the constant term a0. Right? So this is the logic that we have used in our procedure for calculating integer roots. But remember here that all these coefficients must be integers. So for example, if I give you a question like this, which is a question from Sitzeder and Hammond, if I say find all the integer roots of half x cubed minus x squared plus half x minus 1 equal to 0, remember you can't use the method that I just outlined for the previous problem here straight away, because half is not an integer. So first of all, what we'll do is we'll multiply both sides by 2 to get coefficients which are all integers. So once we multiply throughout by 2, what do we get? X cubed minus 2x squared plus x minus 2 is equal to 0. And then you can proceed the way I just explained in the previous example. So we'll take the minus 2 to the right hand side, and our equation will become x times x squared minus 2x plus 1 is equal to 2. And here also, because we are claiming that x and x squared minus 2x plus 1 are both integers, the product should also turn out to be 2. So in that sense, 2 must be divisible by both x and this expression in brackets, which is to say that x must be a factor of 2. So here all possible integer roots must be factors of 2, which is to say that the potential candidates here are plus minus 1 and plus minus 2. And here again you substitute all these values into the left hand side of this equation where we've taken x common, and you will find that it's only x equal to 2 that fits the bill. It gives us on the left hand side the value 2, which is the same as what we have on the right hand side. The other candidates will not give us 2 on the left hand side. So this is something you can try on your own. Okay, now let's see how these integer roots come in handy. Suppose we look at this question. Write the following polynomial as a product of linear factors. So our polynomial is q of x equal to 2x cubed plus 3x squared minus 18x plus 8. What I'm going to do now is, because it's not so straightforward to factorize a polynomial and write it as a product of linear factors. So what I'm going to do is I'll first try and see if I can come up with a root, and if luck will have it, come up with an integer root. So let's see if we can get an integer root here. Possible integer roots of the equation 2x cubed plus 3x squared minus 18x plus 8 equal to 0 would be such that they have to be factors of minus 8, because once I take 8 to the right hand side I get minus 8, and possible integer roots would be plus minus 1, plus minus 2, plus minus 4 and plus minus 8. So once I substitute these values, I can just if I can find even one root, I'll be good, because that will help me proceed with this problem very easily. So if you notice here, 1 and minus 1, substituting 1 or minus 1 does not help, because that gives us a minus 13 or a 19 on the left hand side, which is not the same as minus 8. However, if x is equal to 2, then see the left hand side becomes 2 times 2 into x squared, which is then 8, plus 3 times x, which is 6, minus 18. And then in the brackets we have 14 minus 18, which is minus 4, and minus 4 times the number 2 outside the brackets will give us minus 8. So clearly x equal to 2 is an integer root, and we can say that x minus 2 is a factor here. Therefore, if we look at a polynomial, it can be written as x minus 2 will be a factor. And now what I can do is, to factorize further, I can divide this polynomial that I have, 2x cubed plus 3x squared minus 18x plus 18 by x minus 2. And once I do that, let's look at this process of division. So x would go into 2x cubed, 2x squared times, so I have 2x squared here, and here I'll write 2x cubed minus 4x squared, because minus 2 times 2x squared is minus 4x squared. Now, as you would all know, in division you have to change the sign of this bottom row, so that will cancel off the first set of terms, and in the second we'll have 3x squared. In the second column we'll have 3x squared plus 4x squared, which is 7x squared, and then we bring down the minus 18x. Then once we do that, we see that we have 7x squared minus 18x. X goes into 7x squared how many times? 7x times. So that then gives us 7x squared, and then minus 2 times 7x will give us minus 14x. Again change the sign, so the 7x squared terms will get cancelled, and you'll get minus 18x plus 14x, which is minus 4x. And then bring the last term in the polynomial down, which is 8. So you get minus 4x plus 8. And now when you look at minus 4x plus 8, x will go into minus 4x minus 4 times. So you get minus 4x here, and minus 2 times minus 4 is plus 8. So you can see we get a remainder of 0. And that is exactly what was implied by the fact that we found x minus 2 as a factor. So that will leave a 0 remainder. And so now our polynomial can be written as x minus 2 times our quotient, which we got from the division process, which was 2x squared plus 7x minus 4. And this you can further split up, the quadratic portion you can further split up as 2x squared plus 8x minus x minus 4, which then gives us below, if I take 2x common here, 2x times x plus 4 minus 1 times x plus 4, and that then gives us q of x as a product of linear factors, which is x minus 2 times 2x minus 1 times x plus 4. So here you see, if integer roots exist, the information on integer roots can really be helpful to solve problems like this one. Okay, there is a theorem relating to polynomials, and this theorem is called the remainder theorem. Let us try and understand what this theorem is all about, because it gives us some very interesting results. So to see this, please take a look at this slide. Let us suppose p of x and capital Q of x, these are both uppercase letters, these are polynomials, and the degree, these are polynomials such that the degree of p of x is greater than or equal to the degree of q of x. So if this is the case, then there always exist unique polynomials lowercase q of x and r of x, such that we can write the polynomial p of x as lowercase q of x times capital Q of x plus r of x. And here, as I'll just show you, this little q of x is nothing but the quotient, and r of x represents the remainder. So let's take a look at this result. Suppose we were doing division the regular way with regular numbers. Let's suppose we were to divide 13 by 3. Then 3 would go into 13 4 times. So that gives us 12. 3 times 4 is 12, and that leaves a remainder of 1. And as you know from your school days, you can write the number 13 as the divisor 3 times the quotient 4 plus 1. Yes, 3 times 4 plus 1, which then gives us 13. So basically this formula is reflecting the same kind of operation that you work with in terms of long division of numbers, regular numbers. So here you have the quotient, little q of x, times the your divisor, capital Q of x, the number the polynomial you're dividing by, plus r of x, which is then the remainder. Now also, if you notice, in terms of numbers, let's see first, the remainder is always less than the number you divide by, because that is the whole idea. If the remainder were higher than the number you were dividing by, then you could have done further division. Clearly, because you have to stop here, it means that the remainder has to be lower than the number you divide by, which is 3. You can use the same logic for polynomials, and you can say that the degree of r of x will be less than the degree of capital Q of x, which is the divisor, because that would then represent the fact that Q of x can't go into r of x anymore. Now, our expression here is P of x is equal to little q of x, which represents a quotient, times the divisor, capital Q of x plus r of x. If capital Q of x is not equal to 0, then I can write P of x divided by Q of x, and this represents our division, where I'm dividing P of x by Q of x, as the quotient Q of x, little q of x, plus r of x divided by capital Q of x. Please note here that if the remainder is equal to 0, so if this term vanishes, r of x by q of x, because r of x is 0, we say that capital Q of x is a factor of P of x. When I use the word factor, it means that if I were to divide P of x by Q of x, it would leave a 0 remainder, and that's precisely what we are saying here, right? Now suppose this capital Q of x is given by x minus a. Okay, it's a polynomial of degree 1. Now in this case, we will write our polynomial P of x as little q of x, which represents a quotient, times x minus a, because that's the expression you're now dividing by, plus the remainder, which is now going to be r. This is because if you're dividing P of x by Q of x, we are saying that the remainder always has to be, the degree of the remainder always has to be less than the degree of the divisor. So because the divisor here, Q of x, capital Q of x, is x minus a, the degree is 1. So clearly the remainder has to be a constant. In this case, it has to be of degree 0. Okay, so if P of x, that's why I have not written r of x, I have written r here, it is a constant. So P of x is equal to little q of x times x minus a plus r. Now this then gives us a very interesting result, because the moment I substitute x equal to a in this equation, what do I get? I get P of a is equal to nothing but the remainder. And actually this is a very useful result, because and why is that so? Because suppose I were performing, I was looking at this division operation, let's look at this example 3a, where I'm dividing 3x squared minus 4x plus 6 by x minus 1. Now suppose I'm not interested in the quotient and all I want is the information on the remainder, then all I have to do is just substitute 1 into the main polynomial, which is 3x squared minus 4x plus 6, and by the remainder theorem we'll get the remainder here. So look here. So if I substitute x equal to 1 in the polynomial P of x, I get P of 1 is equal to, by the remainder theorem, that's nothing but the remainder. So that then gives us 3 times 1 minus 4 times 1, which is minus 1, plus 6, which is then 5. So the remainder here is 5, and you see the beauty of this, that you don't even have to perform the entire division. You just have to substitute that value 1 and you'll get your remainder. Similarly, take a look at this example. Suppose you have to find the remainder for this operation, then again just substitute minus 5 into the polynomial p of x. So if we define the polynomial p of x as minus x cubed plus 4x squared plus 3 times x minus 2, and here we substitute minus 5 into this polynomial, I get p is equal to minus 5. By the remainder theorem, that has to be equal to the remainder, which is r, and that's then going to be minus 5 cube is 125 plus 4 times x squared would be 4 times 25, which is 100, plus 3 times minus 5, excuse me, plus 3 times minus 5, which is going to be this is minus 5, so that's going to be a minus 15, and then you're going to get minus 2. So here it looks like these numbers have come out of nowhere. So plus 3x, I'm sorry, here there is a typo, plus it should be plus 3x plus 10. So that will give you minus 15 plus 10, and that will then give you minus 125 plus 100, which is minus 25, and minus 15 plus 10 is minus 5. So that will give you minus 25 minus 5, which is minus 30. Just please check these calculations again, because these numbers have gone a little haywire. Right. So this is the point here is that you can just simply substitute for that number minus 5 and check for the remainder. Right. So that is one result. And just to take this result further, so we have said that if p of x can be written as q of x times x minus a plus r, then if x is equal to a, p of a is equal to r. Let's take this a step further. Here, let us suppose the remainder is 0. Then clearly that means that if I were to substitute a into the polynomial x equal to a, then p of a would be nothing but 0. Okay, so this then leads us to a very important result which reflects what is known as the factor theorem, that p of a equal to 0 is the same thing as saying that the polynomial p of x has a factor x minus a. Or in other words, for the polynomial p of x has a factor x minus a, this statement is equivalent to saying that the value of the polynomial at x equal to a has to be 0. Right? So this corresponds to then a 0 or a root of the polynomial. Okay, now corollary of the factor theorem is as follows. Corollary is basically a result that follows from the main result. A corollary here is that an nth degree polynomial p of x, a polynomial of degree n, can have at most n different zeros. To see this, suppose we have zeros at, let's say, a1, a2 and so on till a sub k. Now these zeros will give rise to a different factor which would be of the form x minus a, right? So in that sense, I can write my polynomial p of x as a of x, which is some polynomial again, times x minus a1, because there's a 0 at a1, so x minus a1 is a factor, x times x minus a2 and so on till x minus a sub k. So clearly if I write the polynomial in this fashion, then the polynomial has degree, it has a degree which is greater than or equal to k, if you look at this expression here. Also, because the polynomial is of degree n, clearly this k cannot exceed n. And in that sense, we say that a polynomial of degree n, because k cannot exceed n, a polynomial of degree n can have at most n different zeros. Okay, so let's take a look at these, some of these examples, and these are interesting in the sense that you get a sense of how to fit cubic functions into certain kinds of graphs. So look at this question here. It asks you to find a possible cubic function for the following graph. Now, if you look at this graph here, this graph touches or intersects the x-axis. You can see here the roots of this polynomial are minus 2, 2 and 4. These are the zeros of the polynomial, and in that sense I can write the polynomial as a product of linear factors x plus 2 times x minus 2 times x minus 4 with a k in front, because if I want to write a general polynomial in this fashion, then I will write it as, in general I can write it as f of x equal to k times x plus k. K may as well be 1, but it could be some other number also, and we will just see what that's going to be. So in general we can write the function f of x as k times x plus 2 times x minus 2 times x minus 4. This is to reflect that minus 2, 2 and 4 are the zeros of the polynomial. Now, if you look at this graph, the value of the function at x equal to 0 is 8. F of 0 is 8. So what I can do is, if you notice here, this point 0 comma 8 has to satisfy this function. Okay, so if suppose if I take k as 1 and I were to calculate f of 0, what would I get? I would get 2 times minus 2 times minus 4, which is minus 4 times minus 4, which is 16. But the point is, at x equal to 0, I want a value of 8. I don't want a value of 16. So what I'm going to do is, I can use a value of k which is equal to half, because once I put k equal to half, then that will satisfy this fourth piece of information. So the three pieces of information I had earlier were about the roots of the polynomial, and this k equal to half will help me factor in the fourth piece of information, which is that the value of the function at x equal to 0 is 8, right? So in this case, k becomes half, and I can write my polynomial as half times x plus 2 times x minus 2 times x minus 4, and that then if you do the algebra, that boils down to half x cubed minus 2x squared minus 2x plus 8, but then you could always leave it as a product of linear factors. So it can very well be written as half times x plus 2 times x minus 2 times x minus 4. Okay, now take a look at this graph. This is something which is interesting, and something that you might have to put in a little thought about. Take a look at this graph. Now here you have a situation where you have roots at x equal to 1 and at x equal to 3, right? Now one way I could write this function could be, okay, let's write it as k times x minus 1 times x minus 3. But note here, there are two things that are going on here. If you look at the behavior of the graph around x equal to 1, the graph changes sign, right? To the left of 1 it is positive, to the right of 1 it becomes negative. But around 3 the graph does not change sign, it is negative. Do you see that? On both sides of 3. So if I were to write this function as k times x minus 1 times x minus 3, it might lead to a problem, because if I were to take some value x less than 3, let's say 2, that would give me 2 minus 3 in this factor here, if I didn't have the exponent 2. So that would give me a negative number. But if I were to take some value greater than 3, which is, let's say x is equal to 4, then I would get 4 minus 3, and that would make the value of the function positive. So clearly I don't want a change in sign, and in that sense I put an even exponent for the factor x minus 3. So in general I can write this function as k times x minus 1 times x minus 3 squared. I hope you understand this point, because at x equal to 1, the graph has to change sign. So we use an odd exponent. For x minus 3, for the root x equal to 3, the graph should not change sign. So the behavior is, you can see it's a kind of a quadratic graph in this region. So here we are using a square. Now sometimes people ask, why not, okay, if you're using a square, you could also use to the power 4 or to the power 6, you could use higher even exponents. But remember, we're trying to fit a cubic function into this graph. So here we need the sum of these exponents to not be more than 3, right? So in that sense we're using 2, we're not using a 4 or a 6, which actually in terms of the graph would have the effect of making the graph flatter. Okay, now another piece of information in this graph is that the value of the function at 0 is given as 18. Okay, it's given the vertical intercept is 18. So 0 comma 18 should be a point on this graph, and if that is true, now suppose I put k equal to 1 and I put x equal to 0, then what will I get? I'll get minus 1 times 9, right? Minus 1 times 9, which is minus 18. So, sorry, which is minus 9. So, if I want to make that 18, then I'll have to multiply this whole thing x minus 1 times x minus 3 the whole squared by minus 2. So, if I put k equal to minus 2, I'll have the graph satisfy this point also, which is 0 comma 18. And in that sense, this would then reflect my possible cubic function for this graph. Okay, before I move on, what happens here is that if you look at this particular function, minus 2 times x minus 1 times x minus 3 the whole squared, in this region where x is equal to 3, I have used the factor x minus 3 the whole squared. This is what corresponds to an even multiplicity, which is to say that the root x equal to 3 occurs twice. It has a multiplicity of 2, and graphically an even multiplicity is what leads to this kind of a graph where the graph does not change sign. So, let's talk a little bit about the multiplicity of roots, because that is something which is coming into our discussion. So, I'll tell you briefly about the multiplicity of roots. Let us suppose that we have a polynomial p of x, which can be written as k times x minus a sub 1 to the power m1 times x minus a sub 2 to the power m2, and so on till x minus a sub k to the power mk. Now, here our factors are x minus a1 which appears m1 times, x minus a2 which appears m2 times, and x minus ak which occurs mk times. Here a1, a2 through ak, these are your distinct roots. But because x minus a1 appears m1 times, we say that the root x equal to a1 has multiplicity m1, right? I'll just give you an example if it's not clear here. But the point here is that here all these multiplicities m1, if the factor x minus a1 appears m1 times, x minus a2 appears m2 times, all these powers m1 plus m2 and so on till m sub k, these have to be exactly equal to n, because we're talking of a polynomial of degree n. Now, we say that if a factor x minus a appears m times, then a, the number a, is a root or a 0 of multiplicity m. Just let's take a look at a specific example to understand this. Suppose a polynomial is given by p of x equal to x minus 4 the whole squared, right? This is a quadratic, as all of you would know. Now, this I can write as x minus 4 times x minus 4. So, we have two factors here, both of which will give us the root 4. So, our root here is there's a distinct root x equal to 4, but it is a repeated root in the sense that it has multiplicity 2. It is the root here, the 0 here is 4, which is occurring twice. And this is something which you can also see in terms of the graph, because if we have x minus 4 the whole squared, you can see here, this is a graph which is just sitting on the x-axis. In fact, this is what happens with even multiplicity. When you have even multiplicity, the graph just touches and bounces off the x-axis, right? But if you have odd multiplicity, when multiplicity is odd, then the graph is going to intersect the x-axis, and that's exactly what we were reflecting in the examples that we just did a little while ago. And this is something because the graph is bouncing off the x-axis. In terms of the discriminant, you would know that the discriminant has to be 0 for a quadratic function if the graph has a repeated root. So, clearly you can see here, if the function is x minus 4 the whole squared, that can be written as x squared minus 8 times x plus 16. So, here what do we see? If we calculate the discriminant, that's b squared, which is 64, minus 4ac, which is 4 times 16. So, 64 minus 64 is 0. Discriminant is 0, and that is why you see that the graph just bounces off the x-axis at x equal to 4. It's a repeated root, it's a 0 here, x equal to 4 is a 0 here with multiplicity 2, right? Let's look at this example now. This is a polynomial of degree 6. You have x cubed times x plus 2 times x minus 4 squared. So what do you see here? The factor x appears thrice. So you have 0 at x equal to 3 with multiplicity 3. You also have a 0 at x equal to minus 2, but this only has multiplicity 1. So you have, in fact, if multiplicity is 1, then we call the root a simple root. And finally, we have x minus 4 squared. Here the multiplicity is going to be 2 for the root x equal to 4. So this way we can get a sense of what how many times the roots are occurring, or how many times the factors associated with those roots are, with those distinct roots are occurring. Let's take a look at this graph. It's a little ugly, but this is how it is, and here let's see what's happening. So if you look at this graph, you have a 0 at x equal to 0, and because you see it's an odd multiplicity because it's x cubed, what you will see here is that it is going to intersect the x-axis. Whenever the multiplicity is odd, you're going to have the graph intersect the x-axis. So you'll see the graph is intersecting at the x-axis at x equal to 0. Now let's look at the factor x plus 2. Here also the graph is going to intersect the x-axis at x equal to minus 2, and this is exactly what is happening at x equal to minus 2, right? And if you see the factor x minus 4 squared, here the graph will not change sign, so it will just touch the x-axis and it will bounce off the x-axis at x equal to 4, because here the multiplicity is even, right? So if you see here, again, because it's a polynomial of degree 6, here if you look at the end behavior, that's up, up. And that is then the discussion that I have for you relating to multiplicity of roots. I hope it has made sense, and you should also read more about it because there's a vast literature available for this particular topic. I've just taken you there, and this can be done in a lot of detail. Okay, so this is what I have for today's lecture, and right, so I won't go any further. I would have liked to do some fun problems, but it looks like we've run out of time, and we've reached the end of the lecture today. In the next lecture, I'm going to cover power functions and exponential functions. So that is the plan of action for the next lecture. Until then, goodbye and take care.